I am Anil Kumar. Welcome to my YouTube channel and the website globalmathinstitute.com. In this video, we are going to discuss a very important topic, which is continuity and differentiability. Whenever we begin with calculus, that is one of our first application of limits and derivatives. Well, in case you want to learn from me, you can always send an email on the address given here. In this video, we'll discuss what is continuity, and in more details, we will see whether a function is differentiable or not in its entire domain or at a particular point. We'll understand these concepts with the help of a quiz, which is just true or false questions. Now, whenever we talk about continuity and differentiability, it does give us examples which are based on piecewise functions. So many of our examples will be piecewise functions. Functions individually could be continuous, but at the point where they are joining, for example, as you can see here, there could be a discontinuity. And therefore, piecewise functions play a very important role. And then, once we understand all these concepts, we will have practice test question. Now, let's first discuss about the continuity itself. For a function f to be continuous at x equals to c, what is very important? There are three things which are very important, and therefore we write a function f is continuous at x equals to c if and only if. This means if and only if, right? So let me write down. These three conditions are met, all the three. So first one is that the value of the function should exist at that point c which we are talking about. Second is that the limit should exist. And third is that the limit and the value of the function should be exactly same, right? So these are the three conditions for continuity. The diagram which we see here, for example, has two different types of curves, and we're looking at this particular point. Let's call this point as C. Now at this point, x value is C. You see that the function is continuous since the two match. So here we see that the limit exists and the value of the function and the limit is exactly same. But there could be examples, just as you saw early on. What we have here is a jump discontinuity. Correct? So that could be possible. Now there are other kinds of discontinuities also. So let me just list the types of discontinuities here. One is jump discontinuity. One is because of a hole. And one is because of a vertical asymptote. We will normally refer this to be as infinite discontinuity. So these are the types of discontinuities. To give you examples of each kind, jump discontinuity is, for example, one function ends here, the other one then starts, right? The whole discontinuity is you have a rational function where we have a common factor between numerator and denominator, and you could have infinite discontinuity, for example 1 over x, So at a given point, we see that the function goes to infinity, right? So that is why you should say here it is discontinuous. So these are the three types of discontinuities which you have seen earlier, and therefore we're not getting into the details of these types. But let me take an example, which is a piecewise function, to elaborate. The question here is explain that the function f of x is continuous at x equals to 2. Now, when we want to show that the function is continuous at x equals to 2, what should we do? Well, the function is given to us and it is x squared minus 1 when x is less than 2 and is minus x minus 3 whole square plus 4 when x is greater than 2. What we need to do is these three things, and that is we should find the value of the function at 2. That is the first thing, which is which is whether f of c exists or not. C is 2 in this case. Then we have to find the limit of this particular function as x approaches 2. If the limit and the value are same, then the function is continuous, correct? So let's say this is at f of 2, we get a value and that is the limit. So this limit should be equal to the value of the function. Only then it is continuous. So as you can see, the two pieces, one is a parabola which is opening up. The other one is a parabola which is opening down. So if I approach from left side, in that case the limit of the function is what? From the left side, we have to substitute the value in the first part of it. So it becomes 2 squared minus 1 and 4 minus 1 is 3, correct? So when you substitute 2 here, you get the limit as 3. You have to find the limit from the right hand side, substituting in the second. So in the first case, we found that this is 2 squared minus 1, which is 4 minus 1, which is 3. And in the second case, we calculated by substituting here 2, right? So we get 2 minus 3 whole square plus 4, which is minus 1 plus 4, and which is also 3. So we see that the limits from left side and from the right hand side are equal. Now, the value of the function is this. So from here, we can find what f of 2 is, and we did see that this is 2, right? So therefore, the limit exists, it is 2. And since the limit exists at x equals to 2 of f of x, and the value of the limit is same, and the limit x approaches 2 for f of x is equal to f of 2, which is in this case 3, the function here is continuous. You understand? So that is how we so if the limit exists and it is same as the value of the function is continuous as explained here, correct? So that part I hope is absolutely clear. You have three conditions of discontinuities, which are jump discontinuity, whole discontinuity, and if you have a vertical asymptote or infinite discontinuity. To prove that a function is continuous at a point, we basically have to prove these three things, right? Now with that in mind, let's move on to understand differentiability. Now when I say differentiability, in that case, we should have a finite value, some real number, as the value of differentiation at that particular point for the given function. So the function f is differentiable at x equals to c if the derivative of f at c has a numeric value, real number. If f is differentiable at every value of x in the interval, then f is differentiable on that interval. So we're talking about two things here. We're saying that if we are giving a function, let us say this is the function given to us, right? In that case, we are looking into each and every point in between, which is differentiable at any point c or within the interval. You understand? So when we talk about interval, within this interval, all the points inside the interval. Let's say the interval is from A to B, right? So this point is at B. Right? So let me call this point as B, f of B, right? And the point here as A, f of A. Then the function is differentiable in the interval A to B. Remember, the function is not differentiable at its corners since the limit does not exist here, correct? You cannot approach from both the sides. That's the concept, right? So the note here is the limits of differentiable function should exist for differentiability. So here is a very, very important criterion. We are trying to find differentiability using the definition of limits. So in this case, if we have to prove that the function is differentiable within a given interval, in that case, we have to actually find the limit of the differentiable function, and it should exist at each and every point within that interval. So I hope you got the idea, right? Let's try to understand with the help of an example. So example here is, explain that the function f of x is differentiable at x equals to 2. So now we are given a function which is exactly what we did earlier. So we have a function x squared minus 1, x is less than 2, and minus x plus minus 3 whole square plus 4 when x is greater than equal to 2. We just checked that this is continuous. However, we now need to check whether it is differentiable or not, correct? How are you going to do that? Let us try to see. So for this function, we already have seen that this is continuous, correct? So we are given the function f of x, let me rewrite, as x squared minus 1 when x is less than 2 and is minus of x minus 3 whole square plus 4 when x is greater than equal to 2. Let's find the derivative of this function. So the derivative of this function is 2x, right? And here we get what? We get minus 2 times x minus 3, right? So 2x when x is less than 2, and it is minus 2 times x minus 3 for x greater than equal to 2. Now, let us see what is the derivative of the function, the derivative of the function. What is the limit at every point in between? That is what we are going to now test. So let me find the limit when x approaches 2 from the left side for the derivative of the function. That is what it is. So when I substitute 2 here, in that case, we get what? We get 2 times 2, which is equal to 4. And let's also find the limit when x approaches 2 from the right-hand side. So in that case, what do we get? Well, substitute 2 here in this particular equation, which is minus 2, 2 minus 3, correct? Which is minus 2 times minus 1 or equals to 2. Now what we note here is that the limit when x approaches 2 from the left side for the derivative of the function is not equal to the limit when x approaches 2 from the right hand side for the derivative of the function, and therefore we say it is not differentiable, right? So it is, this implies not differentiable. Does make sense? So let me write down here. So the function is not differentiable. Is that clear to you? Very important. So what we saw here is this function, which earlier we showed that it's continuous, right? We had shown this is continuous, and whose graph is given here. So at this point, it is really not differentiable. So if you sketch this function, what you find is that one part of the graph is kind of like this, and the other part of the graph is continuous, starts here but goes here. So at this particular point, the derivative is not the same for both the function. So if you zoom it, you'll find that there is a clink kind of a thing, right? And therefore, the function is not differentiable at this particular point. Is this clear to you? It may look like, but when you find, you do get the idea that yes, it is not differentiable, right? As we just calculated. So here is the solution of the same question which we just did. So basically, you take the derivative of the function and on either side find the limit of the derived function, derivative function. Since the limit is different, it is not equal, so the limit does not exist for the derivative of the function. So therefore, the function is not differentiable. Is that clear to you? Perfect. Now let's take another example. Now this is like a corollary. Differentiability also implies continuity. This is important to understand. So if the function is differentiable, then it is continuous at that particular point. So the example here is prove that f of x equals to x minus 1 to the power of 1 over 3 is continuous at x equals to 2. So we want to prove that this function is continuous at x equals to 2. Here's the graph for your reference. We are looking at the point 2 here, and we want to show that it is continuous here at this point. So, well, we have done the other way, which is to show that it is continuous, we found the derivative, whether it is differentiable or not. Correct? So, to show that, you got to find real limits also, right? But we have to prove using differentiable. If the function is differentiable at x equals to 2, then it is continuous also. So this is important to understand. So if you have the derivative, from the derivative also, we can figure out whether a function is continuous or not. That is what we're trying to check here, right? So let's find the derivative of the function. Using the power rule, what do we get? So we use the power rule. We get 1 over 3 x minus 1 to the power of 1 over 3 minus 1, which is minus 2 over 3, times the derivative of inside function, which is 1, right? So let me write down 1 here. Okay. So what we get here, for 2, substitute the value 2. You get the derivative as 1 over 3. Now that's a real number, right? And what we notice is that the function has a derivative. That means it is continuous also, correct? Add 2, correct? Now, if you see it the other way, it is not true, right? For example, if you are analyzing that particular point, as you can see here, so let me write down a note here. That is to say that it is not differentiable here, right? But it is continuous. And therefore, This method doesn't imply that if it is not differentiable, then it will not be continuous. You get the idea, right? The other way, this method cannot be applied. Okay, so this is very important to understand. So now let's look into what we have learned so far. So here is the summary of existence of derivatives. So there are different conditions when the derivative may exist. A function f is said to be differentiable at a if the derivative exists. That is our basic definition. Now, a point where the function f is not differentiable, we can say that the derivative does not exist. Functions are not differentiable in their domain under following cases. So we have a couple of cases here which will give you an idea when is not a function differentiable. So that is a corner. So if you have a corner on the graph, it is not differentiable at that particular point. Or if you have a cusp as shown here. A vertical tangent is normally, in this particular case at origin, we have a vertical tangent. If you have a piecewise function which has a discontinuity, in that case it is not differentiable. So these are many different cases in which the function will not be differentiable. So for a function to be differentiable, the value should exist at that particular point, and then you can actually find the derivative. And the value of derivative should exist. So note, a function is not differentiable at any discontinuity, such as asymptotes or holes, as they are not in the domain of the function, right? So we are considering the points which are in the domain of the function. Now here is a quiz for you based on the learnings. I would like you to pause the video, answer these questions. Question number 1. A function is continuous on a closed interval AB, then it is differentiable in the closed interval AB. Is the statement true or false? Take your time to answer. I'll provide you the solutions of these questions in the next video. Question number 2 here is, a function can be discontinuous but differentiable at that point. Is it true or false? Question 3. A function is differentiable on the interval AB, then it is continuous in the closed interval AB. Is this statement true or false? Question number 4. A function is continuous at x equals to c, then it is differentiable at x equals to c. Whether it is true or false. So when you write your statement, you justify your answer also, right? So justify. That is very important part of learning. The last quiz question here is, a function is differentiable at x equals to c, then it is continuous at x equals to c. True or false? We have actually answered these questions in our video earlier. Now you need to recall and write down your answers. To find the solutions of this, look at the next video. Now, here is your test question based on the learnings of this particular chapter. Now, this is a very important test question which I would like you to attempt. It is based on continuity and differentiability, which we have learned in this particular video. Find a and b to make the function f of x differentiable at x equals to 2. You have to find the value of a and b to make this function differentiable at x equals to 2, right? Not just continuous, differentiable. So f of x is equal to ax cubed when x is less than 2, and f of x equals to b times x minus 3 whole square plus 10 when x is greater than or equal to 2. So hint for you is that there are two unknowns, a and b. Since there are two unknowns, you need two different equations. First one you can get from the principle of continuity, we learned three conditions. Limit of this function should exist and should be the value of the function at 2 in this case. So that will give you one condition. The second one is that the limit of the differentiation of the function should exist. To find the derivative of the function and then find the limit at 2, that should also exist. That will give us a second condition, and so you will get the value of a and b. So I hope that helps. So with this, we'll end this video. I hope you have learned the concepts of continuity along with differentiability and seen how we can actually combine the two and get to know whether a function is differentiable or not. So in this particular video, we have learned that limits can be used to show that function is continuous or it is differentiable. You get the idea. So from the limits, we can actually find both the conditions, and as you now understand, if it is differentiable, it is definitely continuous, correct? So that way also, you can go back as we saw in example 3. You could prove that it is continuous at a given point. So I hope the concept is absolutely clear. You can look into my following videos for the solution of the quiz and also the solution of the test question. Feel free to write to me on the email address given here or check with our website for new updates. Thanks for your time and all the best.